Okay, in this video, we're going to begin 6.2 by talking about the volume of a solid. Our objective in this video is to interpret the volume of a solid using integration. You may be asking yourself, volume? So let's go back to your elementary school days, and we're going to talk about solids. Okay, so some of the solids that we're familiar with are things that we see day to day, such as spheres and rectangular prisms and circular cylinders. Of course, there's all sorts of shapes that we would consider three-dimensional. So they take up space in the world that we live in. Without getting too conceptually deep into it, we understand that they have units that are length cubed. So, for instance, a sphere might be measured in terms of cubic centimeters, and in whatever unit you specifically are talking about. Now, understanding volume, the space that it occupies, right? We usually think about just the formulas that define these quantities. So we know that for a sphere, for instance, the volume is given by 4/3 pi r cubed, where r is the radius of the sphere. So the length of the point in the middle, so the center of the sphere to the surface of the sphere. A rectangular prism, we know, is length times width times height. And a circular cylinder is pi r squared times h. So the development of these formulas, the volumes of solids, is one of the oldest mathematical endeavors. It's resulted in some pretty famous geometric formulas like the ones I have written down here. But there's a way to do this with calculus. What we're going to cover in this video is just one of those ways. But roughly what I want you to keep in mind is that just as before, the way that we calculated area by thinking about taking these infinitely thin rectangles, which were really, akin to just lines, and adding them all up, we can think of each of these as being made up of infinitely thin slices like this. That's one cross section. That have some infinitesimally small area. And once we add all those up using integration, then we'll have a good picture of how to actually set up, how to calculate volume. So first things first, let's develop the integral. And for the sake of clarity here, okay, I'm going to draw some solid that is cut along an axis. So it's cut parallel along an axis with a plane to obtain a cross section. Okay, so here's my solid. I'm just going to draw it in. So you think of this might be a half dome, and then it's lying on the XY axis. That's my solid. And we're going to take some plane of it. So imagine that this is an infinitely thin slice. that runs parallel along to the y-axis. Okay, so it's some distance x from the y-axis. Okay, and it's got an area. So this area depends on x. Okay, where x is a different distance between the plane and the x-axis. And what we're going to think about is each one of these is representative of an infinitesimally thin piece of the volume. But in order to make this rigorous, we're going to construct a Riemann sum first. So what we're going to do is we're going to partition, oops, that's not how you spell that, partition, if this is, say, A and B, that the values between which x ranges, because we're going to add up all these slices and we're going to assume that they actually have some volume. So we're going to partition A and B using n subdivisions. And we're going to have, that's going to give us these slabs of width delta x using sample points x sub I star. This should sound familiar, right? So somewhere in that slab we have this x sub I star. For each, this is the subinterval specifically that we're talking about, the ith slab. And so the volume of the slab is the area at x sub I delta x. Okay? And this makes sense, right? Because we're thinking about this slab as it has some tiny thickness, and the area, right, it makes it a prism. It's a very thin prism. Now, when we set this up, remember that to actually find the total volume, that's going to be the sum of the volumes, so of the VIs. That's going to be the sum from I equals 1 to n of A of x sub I star delta x. And then the limit of the Riemann sum, so in the limit, the volume is actually going to be the limit as n approaches infinity of the sum from I equals 1 to n of these A x sub I stars delta x, which is just going to be the integral from a to b of a of x dx. So really this piece right here, this is the infinitesimally thin slice that we're going to take and integrate every time we do one of these calculations. And to illustrate this, we're going to do a time-honored calculation of the volume of the unit sphere. So bear with me as I set up the picture here, okay? So I have in 3D space, we're not going to get too into it right now about what it means to be in 3D space, but I have the unit sphere, That doesn't look very good. No, let's try that again. In fact, let's start all over again. Sometimes this happens. Sometimes we need to just recalibrate, right? So I'm going to set up again I'm not going to add the third axis to avoid confusion. So it's just going to look like this. And like this. Undo that. Okay, so roughly that's our sphere. Now we're going out to 1 and -1 on both axes. Okay, that's the y-axis and this is the x-axis. All right, and our infinitesimally thin slice is going to be this cross section, which is actually a circle centered along the x-axis. Okay, so imagine that you're taking many of these and you're adding them all up. Okay, so let's think about what we're doing. So each cross section, so our cross section is a circle, and it depends on x, right? So let's think about what we're actually looking at here. So what is the area of this cross section a of x? Well, if we think about how this radius is set up, right? That's where it crosses the y-axis. So we need to think about this picture right here. I'm going to have to set up another axis here. So here's the x-axis and here's the y-axis. And I'm going to try to draw as best as I can a semicircle. No, that didn't work. It didn't like that. No. Come on, do a semicircle. You can do it. Okay. It's not gonna let me. So I'm just gonna do it by hand. So here's my semicircle. All right. So this is how it looks like when you're looking at it from up above. So here's y, here's x, here's 1, here's -1, here's 1. Okay. Now, so how does y depend on x along this curve, right? What is the equation of this curve? The equation of this curve is y equals square root of 1 minus x squared. Correct? Correct. Okay. And so when we look at the cross section here, right? So something like this. It's crossing like this, and then if we imagine that we're directly overhead, then that means this is the radius. So the radius is the y value at that point for x. In other words, a of x equals pi of radius squared, right? Because it's a circle. That's the area of a circle. The specific radius we're talking about is pi y squared, and we know that y equals the square root of 1 minus x, so we're actually looking at pi of 1 minus x squared. Okay, so that's our a of x, which means our infinitely thin slice is actually going to be, so infinitesimally is going to be a of x d of x, which is going to be pi 1 minus x squared dx. So that's the area of this infinitesimally thin slice. So that's this area. Now we just have to integrate all of those for x being ranging between -1 and 1. So, and then the next page I'm going to set up, remember that the total volume then is going to be which means this is going to be the integral from -1 to 1 of pi 1 minus x squared dx. All right, now we will go into the calculation in the next page, okay? So the area, I'm going to write it again for the sake of completeness, making sure that you don't get lost here. All right, so remember, the pi can just come out. That's not a problem. So pi integral from -1 to 1 of 1 minus x squared dx. And so this is just polynomial. This is going to be pi bracket x minus x cubed over 3, close bracket, -1 to 1. Using FTC2, what can we do? We're going to do pi 1 minus 1 over 3, because the 1 cubed is just going to be 1, and that's over 3, minus pi, I'm just distributing the pi, -1 minus -1 cubed over 3, which is going to turn this into the same thing as the 1 minus 1/3. So we're going to actually end up with pi 1 minus 1/3 plus pi 1 minus 1 over 3. And that is the same thing. So let's just write it as 2 pi 1 minus 1/3. And of course, 1 minus 1/3 is 2/3. So it's going to be 2 pi times 2/3, which is 4 pi over 3. So this is saying that the volume enclosed by the unit sphere, so that means radius is 1, is 4 pi cubed units cubed, 4 pi over 3 units cubed. And how we did this is we just took the unit sphere, and we took things that looked like the cross section here. Oops, that's not what I wanted. We took things that looked like this, which are just, of course, these are just circles, okay? And we added all those areas up. And of course, in the way that we're looking at it here, this is like almost the top-down approach. So we're looking at, here's x and here's y. But that part doesn't matter. Regardless of what coordinates we chose, it should be the same, right? All right, so the whole point of this is that this idea of taking cross sections, these slices, we can actually make this very versatile. And in the next video, we're going to talk about how we apply this to solids over a